how to produce squeezed vacuum squeezed states of light, squeezed entangled photons, well, you name it. So he's been there for a few years now, a few decades probably. And well, so he has kindly agreed to give a couple of tutorials on these topics, and looking forward to hearing from you. Okay.
Thank you very much, Gabriel. Thank you.
Oh, by the way, he's in NBC, so if you have any questions or anything,
yeah, it will be a pleasure to talk to any one of you. Actually, as Gabriel explained, I did my PhD at this university here, which is the Catholic University. And by the way, I think this year we'll complete 30 years that I defended my thesis. So the decades that he talked about, there are now 3 decades that I have been working on this subject of quantum optics. And then it evolved to quantum information, to structural light, to quantum structural light, and many different stuff. So this is a picture of the Rio de Janeiro area. So in Rio de Janeiro, we have this big bay that is the Guanabara Bay. This is the entrance of the bay. This side of the bay is Rio de Janeiro, and the other side is another village called Niterói. My university, which is the Fluminense Federal University, is located in Niterói. Okay. So we are nearby Rio de Janeiro, but we are not in the city of Rio de Janeiro. We are in the Rio de Janeiro state. Okay. So these are our funding agencies, the Brazilian funding agencies, the different ones. This is the one from the Rio de Janeiro state. And we also have some projects that are in collaboration with the people from São Paulo, which is also funded by their funding agencies. Okay. So the idea of this talk is essentially to match the ideas of quantum optics to structured light. Okay, so how we can manipulate and shape, especially shape the spatial distribution of correlation between photons. Okay, and this is something that was not thinkable at the time I was doing my PhD, because we could not count on so many technological developments that we have nowadays. Okay, but now with the spatial light modulators, DMDs, and so many devices that we have to shape the spatial properties of optical beams, we can do things that we couldn't even imagine at that time. So the idea of this talk is really tutorial. So I'm going to speak very briefly about structural light, what we consider structural light. I will revisit the field quantization and the electromagnetic field quantization, and now using the freedom of taking different modes, different spatial modes, okay, in order to define the quantized field, so that we can somehow incorporate the ideas of structured light in the quantum description of the field, okay? So then I will show that by using more general spatial modes, we can easily compute, for example, spatial distribution of quantum noise, and how to, for example, shape the quantum noise spatially, okay? Then I will, this first talk, I will end with this, the concept of optical parametric amplification and oscillation, which is an essential device for generating quantum correlated beams. Okay, so this is the streamline of this talk. Next week I will go more to the phenomenological part and see and discuss the many different kinds of experiments and measurements that have been done employing spatially structured beams and their quantum noise. Okay, so what about structured light? So this term structural light started to be coined when people started to produce beams with this kind of very funny wavefront. These beams with twisted wavefront, which are orbital angular momentum carrying beams. Okay, so in this sense, we can see that the angular momentum carried by the electromagnetic field that is usually, especially in basic courses, associated with the polarization state of light. This can also be transported with the spatial structure of the beam. Okay, so by shaping the wavefront in this helical part, we can also have angular momentum even if the beam is linearly polarized. So it's an angular momentum that is imprinted in the spatial distribution of the field and not locally in the polarization state. Okay. Now, what happens is that in the paraxial approximation, so in the approximation that we are describing a well-collimated beam, the angular momentum in this context can be separated in a spin part, which is related to the polarization, and this orbital part that is related to this wavefront, twisted wavefront. Okay. So there are many different ways of generating these beams, and most of them are holographic. So you shine a regular Gaussian laser into a forked grating like this one, and then the diffraction orders, they are like twisted wavefront beams. Okay, so they are orbital angular momentum carrying beams that you can, for example, measure this kind of twisted wavefront through these spiral interference patterns, for example. Okay. And well, in the beginning, we would use films that were very delicate to generate these beams, but nowadays we can count on a spatial light modulator that can take more powerful beams, can shape more powerful beams. Now, from the theoretical point of view, how can we conceive this kind of beams that carry orbital angular momentum? So we start with the paraxial wave equation. So it's the wave equation in the regime of paraxial propagation, a collimated beam. So and this we can see that it looks like the Schrödinger equation in the sense that it's a second order derivatives in the transverse coordinates, and there is a first order derivative along the longitudinal coordinate with an imaginary factor multiplying this derivative. So it's formally equivalent to the Schrödinger equation in a situation where the longitudinal coordinate plays the role of time. So in this sense, we can think in this regime, the diffraction is completely analogous to the spread of a Gaussian wave packet in quantum mechanics. Okay. So we can think like this in this way. This equation, this paraxial equation, when we solve this paraxial equation in rectangular coordinates, Cartesian coordinates, or cylindrical coordinates, we have different families of solutions. Okay. In cylindrical coordinates, we have the so-called Laguerre-Gauss solutions. Okay. And in these solutions, we can cast the orbital angular momentum carrying beam. So they naturally appear as solutions of this paraxial wave equation. Okay, so these are beams that have this twisted wavefront and that propagate with this carrying this kind of orbital angular momentum. Okay, but there are other properties of the beams like radial structure also. Okay, and for the Hermite Gaussian modes, we have a different family. A family of modes that are essentially, as the name suggests, they are products of Gaussian by Hermite polynomials. So in all these modes, in both families, they can be cast in a hierarchy of orders, mode orders. So we have different mode orders here. And what is interesting is that obviously there is a unitary transformation that brings one family into the other. And this unitary transformation is block diagonal in the sense that it only connects modes in the same one. So if we focus our attention in the first order here, for example, we can realize an SU2 symmetry, the same symmetry of polarization, okay, in which the Hermite Gaussian modes, they play the role of linear horizontal and vertical linear polarization, and the Laguerre Gaussian modes, they play the role of circular polarization. Of course, you can have any kind of superposition and something that also resembles elliptical polarizations. And this is actually the realization of SU2 symmetry. Okay. And of course, these in the Laguerre-Gauss beams, we can identify solutions that have angular momentum, orbital momentum. Okay. Now, let's go to this subject with this matter of fluid quantization and detection. Okay, so the idea is that if we usually, so I'll go back to the very basics of fluid quantization. Okay, so we start with the wave equation for the vector potential. Okay, and then so this is the path we usually follow. Okay, we go to the variable separation in a spatial part and a time-dependent part. Okay, and then we obtain Helmholtz equation for the spatial part and this harmonic equation for the time-dependent part. Okay, and without in the absence of charges or currents or of sources, okay, the scalar potential can be considered equal to zero. So all the physics, all that we have to describe here can be described in terms of the vector potential. So this is the main idea. As we can see, the two parts of the electromagnetic field, the spatial part and the time-dependent amplitude, they have independent equations. They have those equations for the spatial part and a kind of harmonic oscillator equation for the time-dependent amplitude. So this part here, Helmholtz equation, is where there is room for discussing the spatial properties of the modes, of the beams, and how we can incorporate properties of structure light in the quantized field. So the main idea is, okay, we have the Helmholtz equation, okay, and the solutions of the Helmholtz equation themselves, the solutions, they form a vector space of modes. Okay, the vector space of solutions of the Helmholtz equation is a vector space of modes, are the modes themselves. Okay, and of course I can find the solution in different kinds of coordinate system or with different methods, and I end up with different kinds of modes. Okay, so plane waves, cylindrical waves, spherical waves, or even paraxial waves. Okay, so the idea is that, note that these functions, they are vector functions. So in this case here for plane waves, we have this exponential, this traveling wave solution for the spatial part, and the unit vector that is just a polarization vector orthogonal to the propagation direction. But there is something that is interesting. Okay, if you look at the other solutions, for example, cylindrical or spherical solutions, you see that actually these polarization vectors, they are not independent of the coordinates in the spatial part. Okay, so there is an intrinsic non-separability between the polarization part and the spatial part in solutions that other than plane wave. Plane wave is the only solution in which the polarization is almost completely independent of the spatial part. It's not completely because it's still transverse. It's still transverse. In the Paraxial approximation, okay, we treat the polarization as an independent degree of freedom, but this is valid only under Paraxial propagation. Okay, if we have scattered light, then it's no longer valid. So all these modes, they have the properties of orthonormality and the completeness. And so this is the closure relation of the modes. Okay, so this expresses the fact that any square integrable function in 3 dimensions can be decomposed as a superposition of these modes. So by choosing appropriately these modes in the quantization scheme, we can, how can I say, adapt our theoretical construction to the experimental condition that we are dealing with, okay, to the boundary conditions and detection conditions, especially. Oh. Now, The quantized fields, they just appear like that. So we essentially, what we do is this for the vector potential, the time-dependent part. So we go back to the field, we combine each spatial mode that we have chosen with some time-dependent function or a solution of the harmonic function or the harmonic equation for the vector potential. And the most general solution are cosine and sine functions with some amplitudes x and y here, okay? And in the canonical quantization, these amplitudes here, they are the canonical conjugate variables that are made, transported to operators that do not commute. They satisfy this canonical commutation relation and the corresponding uncertainty principle. Okay, so you cannot have arbitrary in the quantum description. You cannot have an arbitrary information of both quadratures at the same time. Okay, so however, from this vector potential, we can derive the electric field, the magnetic field, and all the rest. Okay, so the Heisenberg equation, this I plugged here, actually the Heisenberg equation, equations for the canonical variable, the quadratures. Okay, and in terms of these quadratures, we can build the so-called annihilation and creation operators. Okay, so these are the operators that, in the formal theory, we use to create and annihilate forms. Okay, and build the Hamiltonian, the energy, and their eigenstates that are the Fock states. So states with well-defined photon numbers. Okay, well-defined photon numbers. Now, we have this. This is the expression for the electric field. Okay, so if we take from the vector potential, we calculate the electric field. It has this expression here, and as we can see here, this part is the part that depends with exponential of minus I omega t, and this one with plus I omega t. So we call this part here the positive frequency part, and this part here the negative frequency part. Okay, so this is the way we name. So you have to recall that the positive frequency actually has a minus omega t here, but it's okay. So it's the usual naming of these objects, okay? And actually, this separation between the negative and positive frequency, it's very important because one part depends on annihilation, photon annihilation, and the other on photon creation. And this has an important role in detection, in the detection theory. So most detectors, they work like this. So you shine a signal on the detector. The detector is initially, so it has maybe some ground state and a continuum of excited state. Once the signal hits the detector, an electron is excited to this continuous state, and then is very quickly excited, creating for example, if it's a semiconductor junction, it creates a pair electron hole that will feed a current, okay? And it can be amplified to produce current pulses, okay? So the main idea is that actually you see that the detection in this scheme is involved in annihilating photons from the field. So it's a destructive process, okay? So what happens is that the coupling between the electromagnetic field and the detector is like in the dipole approximation would be like this, where this is the dipole operator for the detector, and this is the electromagnetic field. If we, in the Heisenberg picture, we build this product here, we will see that we have all kinds of frequency combinations, okay? And we do usually the so-called rotating wave approximation, in which you remove all the fastly oscillating contributions and retain only the slowly varying contribution. So this makes the following. In the rotating wave approximation, you can have only, if you have only these terms here, okay, which means that either you annihilate a photon from the field and excite the detector, or you create a photon on the field and de-excite the detector. But the detector is always prepared in the ground state. So it doesn't have any energy to give back to the field. And also, when it's excited, it goes back to the ground state very fast by other decaying mechanisms, not the interaction with the field. So the only thing that the detector can do with the field is remove photon, nothing else. Okay. So this is the main idea, and this is a very crucial concept in photo detection, the quantum theory of photo detection. Okay. So in this sense, actually, what you see is that the probability of detecting a photon at some given point in some given time will be proportional to these matrix elements. Okay, the transition matrix element for the field, the transition matrix element for the detector. Okay, and if you add all possibilities for the final here I wrote it in the wrong sense. This CI, CF here should be. Oh no, it's okay. CI, okay, it's okay. So if you sum over all possible final states of the field and of the detector, then you end up with this approximate expression for the detection probability, which involves only the part of the electromagnetic field and the initial state in which that is hitting the detector. Okay, so you see, this is quite natural. You see, you have annihilation to the right, creation to the left. Okay, so you have to, in this sense, the detection process is annihilating photons from the field. Okay, and what the detection probability gives you, or what the detector gives you, is this kind of information about the electromagnetic field. Okay, so you have annihilation operators to the right, creation operators to the left. It's not full information about the field. There is some part of the field that you are not seeing. Okay. Let's go, for example, so, and this is quite natural because in the quantized field, okay, you have, for example, the quantum vacuum. We know that the field as an ensemble of oscillators in this quantum description, the electromagnetic field is considered as an ensemble of harmonic oscillators. So they have 0-point energy, okay? And this is the vacuum energy. And of course, since the detector responds to photon absorption, it cannot absorb energy from the vacuum. So if there is vacuum state here, the annihilator operator will acclimate, and this will give a new norm vector. Okay, so this gives you 0. Probability of detection of the vacuum is 0, which is obvious. Okay. Now, what if we are to measure two-photon detectors, two-photon detections? Okay, so I want to calculate the probability of detecting a pair of photons. Okay, one at position R time t, the other one at R prime time t prime. Again, we will have this kind of sequence here. The detector initially in the ground state gets excited by taking photons, quickly go back to the ground state. Get excited by taking the second photon, quickly go back to the ground state. Okay, this relaxation of the detector has nothing to do with the electromagnetic field. It goes down through other relaxation mechanisms. So again, this you will end up in the probability calculation. You will end up with an expression like this: annihilation operators to the right, creation operators to the left. Okay, so this means that with your detectors photodetectors, you can only see this special kind of correlation functions of the electromagnetic field, which are correlation functions in normal order. That's what the detector sees. It doesn't see the full information about the electromagnetic field. Okay, it sees only this correlation in normal order. So this is what we measure when we are measuring intensities, we are measuring individual photon counts, when we are measuring photon pair counts, okay? Always correlations in normal order. Yeah, sure.
Why you assume that the detector behaves like a two-level system and then cannot absorb two photons?
Yeah, okay, good question. Thank you. Yeah, actually, most of the common detectors, they can only absorb one photon at a time. Now, it's another, how can I say, technological novelty. So they are now actually developing new detectors that are able to at once, okay, get two photons or more photons. So those are the so-called photon number resolved detectors, okay? So it exists. The theory is more general, okay? But this theory is for the old-fashioned detectors that only detect single photons at a time. Yeah, very good question, thank you. So now we grab the idea that what we are going to measure are correlation functions in normal ordering. We can put the spatial properties, okay, into play and see what we can do with that, okay? Now, for example, let's suppose I will now compute the single photon detector, single photon probability, detection probability, okay? So this is just, I have a detector, I'm sending a signal there, and I want to compute the single photon probability, detection probability here. Then what I have to do, I know that's that probability, which is, I have calculated before, it's essentially this P probability density of calculating, of having a photon detection at R and T, is this normally ordered function here, which is in the second order, or first order in the positive frequency part, okay? And the overall probability has to be integrated over the surface of the detector. I integrate it over the surface of the detector, everything, okay? Now, if I plug the expressions for the positive and negative frequency part in here, I end up with a sum of matrix elements of this kind, A dagger mu, where mu and nu are indexes that identify the modes, different modes, okay? So I see here that I have cross terms between different modes. But what happens when I integrate, let's suppose that I'm using the paraxial modes. The paraxial modes, like this laser here, it has some waste. It is for a few millimeters. If I have a detector that are a few centimeters diameter, it's virtually infinite compared to the beam. So I can think that this detector here, I can treat it as virtually infinite and do this integration over the whole space, all transverse plane. Then it will give me the delta function. I will use the orthogonality of the modes, and this orthogonality will kill the cross terms. And what I have is that actually the probability, the photon detection probability is just proportional to the sum of the number of photons in each mode, independently. So far, so good. But if the detector surface is finite, then I cannot use the orthogonality condition. Okay, then I start to have cross terms that appear. I start to be sensitive to interference between the different modes. Okay,
And how could you define the is not finite? How many centimeters, millimeters, and so on and so on?
well, well, let me go to the next transparency. I will give you. Okay, so I took this example here. Okay, I take a very, very simple state, one photon state. It's a one photon state. It has only, it's a one photon, which I don't know whether it's occupying a Laguerre-Gaussian plus or a Laguerre-Gaussian minus, okay? And the two possibilities are superposed here with a factor I. All these U plus and U minus here are the Laguerre-Gaussian plus and minus modes with linear polarization X. So the total probability distribution should be proportional to the total photon number, the average photon number, which is 1. I have, in average, 1/2 photon per, in average, 1/2 photon per mode. So a total average number of photons of 1. But now, what if I block? So suppose I have a beam that is like has a waist of 2 millimeters, and I have a detector that has, for example, 2 centimeters. Okay, so it's much larger than the beam width. Okay, but now suppose that I block 3/4 of the detector, and I only look at 1/4 of the detector. Okay, so this 2 millimeter beam, like 3/4 of the beam will be put out of the detection area, and I will only detect 1/4 of the beam. Then what happens is that, okay, when I calculate over this detection surface here, these cross terms, I don't have more 0. I cannot use anymore the orthogonality. They will give some contributions, okay? And now, if you compute the probability of the detection probability here, it will be proportional to this quantity here. Okay. Of course, I'm not saying that you are increasing with respect to the total. There is other part that is being uniformly cut. Okay, but you see that actually, if you take this sector here, and you rotate, for example, this the detection probability will not be uniform. But you see, actually, if you compute the spatial distribution of the detection probability, it looks like that. So this is why then you cut the beam like this. So you just detect this part. Then this is why you are leaving out one bright area, but you are leaving out also 2 dark areas. Okay. So, but then actually, it's not very surprising, because if you calculate the interference of this Laguerre-Gauss beam with this Laguerre-Gauss beam with an I factor, what you obtain is exactly this. Even in classical optics, okay? The quantization here is giving you some interesting result, but it's not giving you anything apart of what you would obtain with classical optics. Okay, so even only the spatial distribution is this. Okay, now let's go to a less intuitive situation. The less intuitive situation is the 2-photon detections. Okay, now suppose that you are going to compute the detection probability, the probability of detecting 2 photons in 2 different locations of the detector, like the camera that Miguel got, okay, R1 and R2. So what happens is that this is...
You mean simultaneous detection?
Yes, simultaneous detection, okay, so they will be made in coincidence, actually. So then what happens is that this average is proportional to the normally ordered intrinsic correlation between the 2 points. So this is the the way you calculate this average, okay, normally are the correlation functions. Again, you have to integrate, okay, and then you integrate over the detector surface twice, one for R1 and one for R2, okay? And well, usually this, if you have in that case like two modes, and you are going to compute here, you see that you have two modes here, two modes here, two modes here, it would give you 16 terms. There is some easier way to compute this is to realize that this part here is the emitting conjugate of this part here, and what you are actually calculating here is the norm of some vector, which is this part acting in the initial state. So it makes it's just a calculation, how can I say, technique, okay? Now, what if we do this technique to the same two modes that I mentioned before? I have Laguerre class, no, not the same two modes, I'm sorry. I was doing it with the same two modes, but then I found that it was more interesting to deal with this one. So this is a Laguerre-Gauss +1 mode, and this is a normal Gaussian beam. This is a normal Gaussian beam, okay? Now, I prepare this kind of state. Suppose I can prepare this kind of state. I generate either 2 photons at the mode plus, 0 photons at mode 0, or the other way around. I put the 2 photons at the Gaussian mode and 0 at the Laguerre Gaussian, okay? With a minus sign here. And then I only write in the electric field the modes that I know that are occupied, that can be occupied. Those modes that are in vacuum, I don't care about. Okay? They will give 0 contribution to the probability. And then what I did here is that instead of doing all the calculation, I just plotted the result of the probability. First, the single photon probability distribution. The single photon probability distribution would be this one. So this beam here would give you counts, single counts that are symmetric, completely symmetric around the propagation direction, okay? Now, what about 2 photon probability, okay? And here I took 2 possibilities to compute, to plot, to make a plot of 2 photon probability. I must fix the first position and then plot the probability of the second detection as a function of the second position, okay? So what I did here was to fix the first position here. So Miguel takes his camera, first he counts photons, individual photons. He will take this one. Then he takes 1 pixel a bit to the right, and he will now count photons, condition to detections on this pixel. It will be this condition measurement, okay? So what happens is that you see that the probability that the second photon is detected close to the first one is 0. So you have no detections around the first detection. And the probability of having the detection on the other side of the beam is increased with respect to the other. So actually, not only you are having, you are actually in this cloud of symmetrically distributed photon counts, okay? You have some kind, in the correlations, you have some kind of spatial order. Spatial order. So the photons are somehow arriving in this one, paired in this one, okay? Actually, if you now fix the first position here at the top part of the beam, then it's the other way around. Then the probability of having the second photon detected close to the first one is increased with respect to the other. So you see that the 2 photon probability distribution is not uniform. And this is a very, very clear and simple example of structured quantum light. Okay? Now, let me now go into this problem of quantum fluctuations in general. So this is for single photon count. But what if we are to measure fluctuations in a more intense ways? How do we compute it? What are the relevant quantities? Okay. So, oops, sorry. So the main idea is that first, we start with the coherent state. The coherent state, so here I have a whole problem here that I haven't realized before. So coherent states are actually eigenstates of the annihilation operator. Why are they so special? Because when the field is prepared in a coherent state, okay, you can see that the quadrature, the two canonical variables, the quadrature, the averages, make the evolution that you expect for a classical field. Okay, so the quadratures, they are just sinusoidal functions of time, okay? And the amplitude is given by the absolute number. So the annihilation operator is not emission. So its eigenvalue is not real. It's a complex number that has some absolute value and some phase, okay? And so what happens is that the absolute value of alpha gives you the amplitude of the oscillation, the quadrature oscillation, and the phase of the eigenvalue alpha gives you the phase of the quadrature oscillation, okay? So in this sense, the coherent states, they are said to be classical-like. The coherent state, by the way, were invented by Schrödinger, okay? Because he was looking for a wave packet that in a harmonic oscillator, a wave packet that would oscillate just a classical part. Okay? So they are an equivalent of they are a quantum counterpart of the classical behavior, if you want. Okay. What is special about them? No, so first thing, they have this average here. The coherent state is a minimum uncertainty state. Okay, so the quadratures they obey the Heisenberg principle, but in the equality. Okay, in the equality, in the bound. So they have the minimum uncertainty, and also the two quadratures have the same amount of fluctuations. Okay, so the fluctuations are the same for the two quadratures. If we go into photon number distribution now, the coherent state is not a well-defined photon number state. Now, if you prepare the beam in a coherent state, you are not having a well-defined number of photons. Okay, and this is very crucial. You very often see people talking about quantum optics like counting photons. And usually the quantum optics setups they have, or the description of the quantum optics experiment have a well-defined photon number. The quantum optics, what I consider the most general quantum optics, okay, is when you are not even sure about the number of photons in your apparatus. Then it's more difficult to understand what's going on. And the coherent state is the simplest case of a state, of a very current state of the electromagnetic field that doesn't have a well-defined number of photons. Okay, so this actually the photon number distribution in the coherent state is a Poisson distribution. Okay? Poisson distribution. The average number is just the amplitude of the coherent state squared. Okay, and the fluctuations. Okay, the interesting thing is that the variance of the photon number is equal to the average photon number, which is typical of a Poisson process. Okay, a Poisson process. It's very important. Now, this is the coherent state. So Glauber, Roy Glauber, who got the Nobel Prize, I think it was in 2005, okay, for quantum optics contributions, okay. And so he invented a phase space distribution, a way to represent the density matrix of the electromagnetic field, okay, in a basis of coherent states. He invented that. Why he used that? Because he knew that photo detection, what happens is that he knew that photo detections only give us normally ordered correlations. And with this function here that represents the density matrix, all normally ordered correlations, okay, like this one here, for example, they can be calculated as if it was a classical distribution. So as a probability distribution. So you just replace A by alpha and A dagger by alpha conjugate. And then what you have here is modulus alpha to the fourth power. And then you just calculate this average using the P distribution, the Glauber distribution of as if it were a probability density, okay? So any correlation function, so if I am to calculate, for example, the fluctuations in n squared, the square of the number of photons, what I have to do if I make this square, it's not in normal order because I have A dagger, A again. So I can use a commutation relation and I end up with these two terms in normal order. So what happens here is that when I calculate this n squared, and if I calculate, for example, the variance in the photon number distribution for a general state of the electromagnetic, and now I'm talking about the general state, any state of the electromagnetic field, I see that I have a variance that is calculated with the P distribution, Glauber distribution, in a usual way, acting as a probability distribution, plus this term here, which is the so-called short noise. This is the short noise, okay? So it's reminiscent to the fact that the electromagnetic field, remember, it came from the commutation relations, okay? So actually the commutation relations is in the realm of the quantization process. So it is reminiscent of the fact that the electromagnetic field is composed by photons, okay? And actually, this kind of separation of the photon detection noise was first proposed by Einstein, in which he said, oh, there is, in this noise, there is part of the noise which can be cast to classical noise, and part of it which is somehow intrinsic to the stream of particles, okay? And actually, but the problem in this, there is something interesting, is that we can treat the Glauber distribution for normally ordered correlation function as a probability distribution, but there is nothing that forces this distribution to be positive. It can assume negative values. It can assume negative values. Well, still we are going to use it to calculate averages. But then if it can assume negative values for those states that give negative values here, you will have this part negative, and then you have a photon number variance that is smaller than the short noise. And this is what we call photon number squeezing. Okay, photon number squeezing. And by the way, just a minute, I will talk about quadrature squeezing. Many people talk about quadrature squeezing, but usually what we are measuring directly is photon number squeezing. We just have make some tricks, some interference schemes to turn quadrature fluctuations into photon number fluctuations and see the squeezing in the photon. Yeah. Right.
So squeezing always is characterized by negative P distribution.
By the well, yeah. No, it's you see, some people, this problem of the classicality or non-classicality of the electromagnetic field this is a big, messy subject, okay? So in the beginning, people said, okay, we can consider this, when this function here is negative, it's a genuine quantum behavior. Some people do not accept that, you know? Because, for example, if you go, there are other representations, other ways to represent the state. And if you go to Wigner distribution, even a squeezed state has positive Wigner distribution. And some people say, no, it's only quantum if the Wigner is negative. So in the beginning, the squeezed state, they became popular because they would give this negative or singular or whatever, okay? And then people say, no, it's not enough. There is some kind of stochastic theory to describe your experiment. You need to look for negative Wigner function. And then a new race started. I should take a look at the time now. How am I? Yeah, so let me. Okay, so I will finish with this next two slides. Okay, so essentially, okay, so essentially we have this. So quadrature noise is computed in this way. Okay, quadrature noise, quadrature fluctuations for Fock states. So we have this. This is the variance for the X quadrature, variance of the Y quadratures. For Fock states, the average value of the quadratures is 0. If you try to compute the average value of the quadrature in a Fock state, it's 0. But there is some there is some fluctuation. Okay, so the variances of the quadratures in a Fock state is not 0. And the Fock states, they are not minimum uncertainty. Their product surpasses the product of their uncertainty surpasses the bound, the minimum Heisenberg limit. Okay. The only state that is a minimum uncertainty, the only Fock state that is a minimum uncertainty state is the vacuum state. Okay, is that one. For the coherent state, I have already mentioned that they have equal fluctuations in both quadratures, and they are minimum uncertainty states. So actually, these fluctuation properties, okay, suggest that we represent these fluctuations in phase space by a diagram in this way, okay, where I can put, I can compute here, for example, the average values of the X quadrature and Y quadrature to define a vector in the phase space, okay, an arrow here in the phase space, and then use the fluctuations to define an ellipse or a circle of fluctuation. For a coherent state, it is a circle. For a squeeze state, it is an ellipse. Okay, and then what happens is that the squeeze. So if we have, for example, that a coherent state, it has a symmetric noise distribution. Okay, in the phase space. So you can deform this uncertainty region mathematically. You can deform this uncertainty region by acting with this operator that is called the squeeze operator. So this is how we describe theoretically, okay, the squeeze states. The simplest one would be acting this squeeze, this operator into the vacuum state. If I acted on the vacuum state, note that here I have this A dagger, and I have an explanation. If I act this operator on the vacuum state, okay, I see that the action of this dagger, A dagger here, will create excitations in the vacuum. Okay, so the squeeze vacuum does have photons. It does have energy. Okay, and energy beyond the vacuum level. So squeezing costs you energy. And this is very important to understand that squeezing costs you energy. And also we see that this operator here, in the power series, the terms of the power series, they are quadratic in the creation and annihilation operator. They are quadratic. So in a sense, this means that you have to, if you want to look to how can I say, implement this kind of operation physically, you must look at processes that create or destroy photons in pairs. Okay, actually, if you act this, okay, on the vacuum state, you end up with in the photon number distribution, in the Fock state distribution, for example, you end up with components only with even photon numbers. You never generate for example, a component with 3 photons or 5 photons or 1 photon. Only 0, 2, 4, 6, 8, and so on. So the squeeze state has only even photon numbers in this distribution. Okay. Of course, there is some people now that generate the A dagger acting on a coherence on the squeeze state, which only has the odd photon number. Okay? So people play a lot with this, but then we have always to look for photon pair creation, and this is where I will stop. The object that will make this photon pair creation in the lab is the optical parametric facility, which I will talk about its behavior and its generation of quantum light in the next week. Okay, thank you.
We have questions. Maybe personal one.
You mentioned semiconductors.
Yeah.
So when you with 1 photon, you excite electron, with them, this electron is going down, emitting photon. But the situation is real materials, semiconductors, they are different, and this process excitation of electron and decay, next step decay of electron, depends on material you use. How do you relate real processes with material?
Yeah, you see, the photon detection theory with the appearance of new materials, okay? So the original photon detection theory was developed actually through photomultipliers, okay? And which is a very old, so it's the photon detection theory was developed by Glauber back in the 50s, okay? So as far as the material behaves in this general way in which a photon creates an excitation that is registered somehow and rapidly decays, then this theory is correct. But now, as he asked, okay, for example, we have other materials and that can, for example, respond to more than 1 photon. Okay, so actually these new materials that you are talking about, they are for these new materials that they behave differently from this general sketch that I showed. You need to do a devoted detection theory for that. So there is photo detection theory that is adapted to new materials. There is this. Okay? It's beyond the content of what I would like to talk.
Once. Oh, so it's time to get.
Ahora vas a venir a se siente todavía queda por dejar alguna cosa.
You mean
Your photon can detect.
Yeah, there's no problem. All you're gonna get is more A and A dagger in this, yeah.
So actually, what Glauber says is that the photon detection theory is proportional to
Yeah.
so you can have a field with n photons.
Yeah, this is true, yeah.
So
You could have here R3, R4, and so on.
So what it doesn't include is two-photon absorption. So because two-photon absorption needs a band gap. And
Yeah.
in Glauber's theory, actually your Fourier detector has a band which is infinite, going from zero frequency to infinite frequency. That's why here the T is the primes.
Uh-huh.
So the intensity is just proportional to the T, to the time of detection. You don't have any washing of that.
Really?
So here, the probability is proportional to T directly, to the time, the exact time when the photon is detected. This is what Glauber, so when you integrate here, it integrates over, so actually, I'm not even sure that you integrate over all final field states, because they are correlated.
Which the final?
So here, so you said before that you are integrating over the material
Yeah.
and the field final states.
Yeah.
But I would say that you only integrate for one of them, because the other is correlated. So if you have
Okay.
one photon, then
Yeah.
so the material changes.
Well, actually, is that you sum up over all possibilities
Exactly.
or find a state of both. Yeah.
But what Glauber did was he took this band and he said, no, the band is going from 0 to infinity.
Yeah.
So I'm detecting any. That's why he could do those intervals very easy.
Okay.
And then he takes those intervals and then, of course, because you integrate over all frequencies with the same probability,
Uh-huh.
then you get this
Mhm.
direct delta. Otherwise, otherwise you would have to correlate. You would have to have an interval with these times.
Mhm.
I mean,
But you see, you mean that it's proportional to the time. Well, I think,
so you have the same time here and here.
Yeah.
Okay? And why do you have the same time here and there? And you don't have an interval over time.
Okay.
This is because the interval is going from all the frequencies from 0 to infinity with the same probability.
Okay.
Otherwise, you would have to have like a convolution.
Okay.
Yes.
Okay.
So what the Glauber modeling of the Fourier detector is, no. I know that there's a band, but this band gap is so large. And I'm only interested in this narrow band of frequencies, that I will take this band and make it infinity.
Okay.
And then that's why you have this band.
Okay.
And the final state, so, as you said, so the final state of the material is just going from, so it's just taking this band down. That's why it integrates over that. What he was integrating is, so what he was, the first one was asking is, what happens if you have a two-photon absorption process? But this is not included in
Because it's first order perturbation. The
because it's
detection,
first order,
yeah.
and also because this band gap in principle is going from 0 to infinity. So actually you don't consider that the first photon is going, that any photon is going to the middle of the band. So everything is absorbed.
Yeah.
That's why.
Yeah. Well, I try to.
No,
I didn't want to go into the details of the
I'm not
quantification.
ready. It's time to
Okay, yes.
okay. It's time to see if what I understood like 15 years ago. And I think that, so the other thing is that this process that you write here actually is dissipation.
Yeah.
This is dissipation.
Yeah.
So this is even in the semiconductors, is the two electrons.
They absorb, yeah.
But
They just go away to
the
make the, just go away to make the curve.
Very nice, Antonio.
Thank you. So I think that this, I put this two-photon, the simulation of two-photon correlation because.
That's really nice. Actually, I did that some years ago, and I never managed to make anything interesting of that.
Yeah.
Actually, I don't think that we did. But it was difficult.
Yeah, I think that with the Miguel's camera, we can do this.
I think so, but actually, well, Miguel is assessing the camera. The Miguel wants to do that in 1 3 per second. Devices.
Yeah. And also, but I don't know, also I thought, why